Hello, welcome to the first sort of overview / summary video that we're going to have in this class. So this first one will be on the whole topic of oscillations. So this is one of the chapters in OpenStax, but it's not quite enough detail. A book that really goes into a lot more detail is the book by French. And these equations come from mostly chapters 3 and 4. Some of the background information comes from chapters 1 and 2, but mostly this equation 2 comes from chapter 3, and then equation 3 comes from chapter 4. I guess background information is number 1, or number 1 could really be probably best found in OpenStax. So like I said, this is a maybe overview or summary video. So overview, just to get a sense of what all of this is about before going into more detail via other videos. Or it's a good summary. So if you went through it and you just want an overview, maybe to prepare for an exam. I've split oscillations into 3 main equations. So we'll go over each of those separately. So number 1, number 2, number 3, and they're kind of in order of increasing complexity. And then I'll talk about sort of how to derive these things, or how we think about solving these equations in general. So really I'm just talking about the solution to those 3 equations and properties of the solutions. And then I'll talk a little bit more generally about how we go about solving these sort of problems. You know, how did we derive this in the first place? Okay, so just to focus on one equation at a time. Landscape. So this first equation, right here, this ma plus kx equals 0. So this really comes from ma, sum of all the forces. So ma is sum of all the forces, and here we're assuming there's only one force acting on a particle. And this is from Hooke's law, this is the spring force minus kx. So if you move the kx over to the other side and you rewrite a as 2 derivatives of x with respect to time, you get this equation. So this is the simplest of all of these. These 2 equations over here are called free oscillations because there's nothing forcing them to move. You know, you displace some oscillator from its equilibrium position and you let go. And either there's no mechanism for energy loss, or there is some damping. This is going to be a damping term in the second one. But both of these are free oscillations as opposed to forced oscillations on the right-hand side here. So for free oscillations, the solution to that differential equation is a trigonometric function. So you could write this a couple different ways. You can write it as a coefficient times cosine plus another coefficient times sine. Or you can just single out one of these trig functions. Here we chose the cosine, and introduce a phase constant in the argument of the trigonometric function. So either way, you have a second order differential equation and there's 2 constants of integration. So in this solution, those 2 constants of integration are represented by the amplitude of the motion and the phase constant, phi. This omega naught is predetermined, though. This isn't a constant of integration. Omega naught is determined from these parameters in the problem, the mass and the spring constant. So given the mass and the spring constant, you know the frequency of oscillations. And this is the simplest case. So again, free because there's nothing forcing it, and undamped because there's not this term right here that exists in this more complicated version of the equation. So given those 2 things, you just have one frequency of free oscillations, which we'll call omega naught. And we put the 0 subscript, the omega naught, to distinguish it from another omega that we're going to see in this number 2. So omega naught just means if there is no damping, what is the frequency of oscillations? So the rest of this picture is explaining why we care so much about this formula. It turns out for any potential energy function, so here I wrote V, but you've also seen U probably for this. For any potential energy function, you can expand the function around a stable equilibrium point via a Taylor series. And the Taylor series is, you'll have a constant. So V near this point is about equal to V naught, and there's no linear term because we're at the minimum, plus 1/2 times some constant times distance from equilibrium squared. and then higher order terms right here. So I didn't write the constant right there, because when you take minus a derivative of this to get the force, the constant cancels out. But this is Hooke's law. This is the potential energy associated with Hooke's law. This is why we care so much about springs. It's because for any stable equilibrium, it has this form. You'll have equations of this form. So not only is it literally just springs connected to masses, you would also use this equation for like a diatomic molecule. So there's some, this molecule could be displaced from equilibrium and then it's just oscillating back and forth, bouncing back and forth. We're also going to use this equation to describe like the position of a simple pendulum. So the form might look a little bit different. Instead of square root of k over m, in that case, the angular frequency is actually mass independent. It just depends on the strength of the gravitational field and the length of the pendulum. But it's a very similar idea in that you have a potential energy function that's quadratic, or at least locally quadratic next to the stable equilibrium point. So something I didn't write down here is that tracking the energy. So the total energy is a constant here as your system is oscillating back and forth. So your energy just keeps going back and forth between kinetic and potential energy. So one of those looks like so potential energy stored in the spring will be 1/2 times k times x squared. So it looks like a constant times cosine squared, and then the kinetic energy is going to be that same constant times sine squared. And when you add those two up, you get cosine squared plus sine squared is 1. So the total energy is a constant there. Okay, so that's the simplest case. To complicate that a little bit, you could have free oscillations, but with some damping. So for most real life problems that you can think of, the system will decay over time. So you might start off with some oscillations, but the amplitude slowly decays over time. So you get an amplitude over time that looks kind of like this. So this is a sign that you have underdamped oscillations. I suppose I'll talk about underdamped versus overdamped in just a second. But so the solution to this, so it's a differential equation that looks very similarly. To solve number one, it's kind of clear that your function, you take two derivatives, you get minus a constant times your function again. It's kind of clear that you get a sine or a cosine. Or at least the teachers tell you it's clear. For this one, it's not quite so clear what the solution should look like at all. So we're going to talk about that at the end, how we actually found this solution. So for right now, just sort of take our word for it that the solution looks very similar to before, except you have an amplitude over time that decays. So it's some amplitude, whatever it was at t equals 0, times this e to the minus something times time, times the original cosine. So I say you could take our word for it, but you could also take this answer and plug it back into the original differential equation and see that it works out. So you should probably do that just to make sure that you're not going crazy with all this, that some of it makes sense. So this decay rate, or the thing related to the decay rate, gamma, it's saying how quickly this thing is decaying, and it's related to that damping coefficient b. So this ratio b over m gives just a new constant called gamma, and the bigger gamma is, the quicker this thing decays over time. One other key fact about this is that you'll notice this frequency is a little bit different from the frequency of free oscillations right here, this omega naught. So we're using a different letter for this. So in other words, if we had free oscillations, it would look like this, and it wouldn't decay over time. And the period would be a little bit shorter. So I'm going to do, but it's almost exactly the same thing. So imagine this thing wasn't decaying. So it kept the same amplitude over time. And the frequency is very, very close to the same, the same whether there's damping or not. So in other words, the period is almost identical right here. But there is a difference. So notice how omega and omega naught are not quite the same. So omega with damping is a very tiny bit smaller. And because it's a frequency, this means the period is a very tiny bit larger than the undamped case. So the difference is so controlled by this formula. Here, generally gamma squared over 4 is much, much less than omega naught squared. So if that's the case, this is a small correction. And as long as this quantity is smaller than this quantity, you have underdamped oscillations, which means that the system does actually oscillate. Even though the amplitude decays over time, you have oscillations. If this is not true, so generally this is less than this, if these are equal, or if the damping, or if this term is greater than the omega naught squared, then you would have critically damped or overdamped motion, in which case this thing doesn't oscillate at all. It just kind of decays exponentially over time. So you might have, like when you look at doors that close and they have dampers, you might see overdamped oscillations where the damping is so strong that the door just very slowly closes and it doesn't actually go past the equilibrium position. But for most oscillations that you can think of, it's still oscillating, just the damping decays the amplitude over time, which means that the energy decays over time. And because energy is proportional to amplitude squared, you have e to the minus gamma t over 2 here, but just e to the gamma minus gamma t over here. Okay, now the final case, the most complicated case, are forced oscillations. So this is the case where you have not only something oscillating, but you have something forcing it to oscillate. So one of the most common examples of this is like a child on a swing. So if the child is, if you displace the child from equilibrium, the child's on the string, the swing, and you're the adult pushing the child. Well, one limit is you not pushing the child and them undergoing free oscillations. So maybe there's no damping and the child just keeps going back and forth, or they slowly decay in amplitude over time. Or maybe you're pushing them, and that's an example of forced oscillations. So the push term, so this is the same equation except changing out on the right-hand side. So we still have the damping term, but this time we have the force of the applied force that's keeping this thing oscillating. And this is a different frequency. So we already have omega naught, we have omega, which includes the effect of damping. And now we have this capital omega, which is how often the oscillator is forcing the motion. So if you're pushing a child on a swing, it's the frequency with which you're giving pushes, right? And so this doesn't exactly match up that case because the applied force is a cosine here. Whereas if you're pushing a child, it's like, this is a spike every couple seconds or so. So we have a more gradual sort of forced oscillation here with the cosine. But it has its own frequency. So this is separate from the omega from this equation. Okay, so keep in mind that the lowercase omega is the free oscillation frequency and the capital omega is the forced oscillation frequency. And this is just an arbitrary phase constant here, this thing alpha. What's interesting is that in the solution, the phase constant is shifted a little bit. So in other words, where the forced oscillation is a maximum, that's not where the resulting oscillation is a maximum. They're out of phase by this thing theta, which we have a formula for here later. So in other words, something's pushing someone on a swing, that push is a maximum, but that push doesn't occur at the same time that the child is at the maximum amplitude. That probably makes sense, right? The push isn't going to be where the child is at the maximum position. It's maybe when they're at equilibrium or sometime before the maximum. What's interesting and maybe not expected right away is this right here. So we're told at the beginning of the problem that capital omega is the frequency of oscillation. So we have capital omega is what you're pushing at, is the frequency with which someone's pushing. And then you have lowercase omega, which is the frequency of free oscillations with damping. It turns out that the actual motion of this object, the steady state motion over time, so in other words, if you wait a long time so that this thing will settle into the pattern that it's going to have over the long term, that frequency is going to be the frequency that it's forced at. So whatever's forcing the motion, that's controlling the frequency of oscillations. And the amplitude is this complicated function. Okay, so this amplitude is not a constant. This amplitude, well, it's a constant if all of these things are constant. But in general, it depends on what the forced frequency is in addition to what the free frequency is. It also depends on the damping, this damping coefficient gamma. It depends on the how big that force is, and then the mass of the oscillator as well. Now this thing theta is another interesting thing. Well, I guess I already talked about this a little bit. The phase of the thing oscillating is not in phase with the force right here. So gamma t plus alpha and then gamma t plus alpha minus theta. So the oscillator lags the force, the applied force, by this angle theta, and this is an expression for the angle theta. Okay, so like I said before, the frequency of the force of the applied force, perhaps you have a knob where you can control that. It turns out that the biggest response, the biggest oscillations that result, is when you force the oscillator near a frequency that it wants to be at anyway. So this is close to the frequency of free oscillations. So remember, as long as the damping is small, the omega and omega naught are the same thing. So you should kind of think of them as the same quantity, even though we see the difference in number 1 and number 2. And the frequency of forced oscillations could be anything. So if you drive this thing too fast, imagine you're pushing a kid on a swing super, super fast. They're not going to get very far. Or if you push too slow, they're not going to get very far. You kind of push them at the same frequency that they're naturally oscillating at. And this phenomenon where the applied frequency is near the natural frequency is called resonance. This phenomenon in general is called resonance. And the response, how sensitive the amplitude is to being on resonance depends on how much damping there is. The lower the damping, the more sharply peaked this is. So this could look like this if there's very small damping. Or if there's a lot of damping, maybe it doesn't really matter so much and it looks like this. Okay, so again, you can plug this into the original differential equation. This starts to get not so fun, right? Maybe you did the first couple, but this one doesn't look as fun. You plug that into this equation to see that it works out. With the trig function, that's not so fun. So you might start to wonder, well, how did we even derive all this stuff? And this is where complex numbers come into play. So we didn't actually need complex numbers to describe the real motion at all. But the complex numbers really help in proving these equations, to see how these equations came about in the first place. It's really hard to guess something like all of this at the very beginning of the problem. So what you do instead is you guess a solution like this. And the only kind of guesswork is, well, that the solution is at this frequency rather than the natural frequency of oscillations. So maybe that's the guess. But other than that, we're not really saying much about the solution. Plug this into the differential equation, just see what you get out of it. So it turns out to make the real part equal the real part and the imaginary part equal the imaginary part, that's what gives you these conditions on the amplitude and the phase of the motion. So you can actually prove this equation. So we use complex numbers as a nice tool to see how this all works out, to prove these equations. And if you're curious why we're talking about phasors also in the context of oscillations, this also gives us another way of thinking about what's going on in terms of the complex numbers. It's a visual representation of the equation, the differential equation, but as vectors in the complex plane. So the word phasor sounds a little intimidating. This just means vectors in the complex plane. Vectors in complex plane. So it's really not so scary. It's just another way of visualizing what's going on. But yeah, this is sort of the starting point for proving the equations 2 and 3. But if you just want to understand the solution, this is what's going on. Okay, if you're watching this just to begin with, good luck understanding all the details here. So you could learn a lot more about phasors, about how to go about proving this, How exactly does the width depend on gamma or beta or B? What are some limiting cases here? You know, what happens if the damping is really small, or what happens if you're on resonance? What is that relative phase angle? So there's a lot of things you can still explore with all of these equations, even with this background information. Okay, great.